Alright, first, all reference equations and tables are from Fundamentals of Engineering Thermodynamics 7th edition by Morin and Shapiro. Alright, let's get started with problem 10.6. An ideal vapor compression refrigeration cycle operates at steady state with refrigerant 134A as the working fluid. Saturated vapor enters the compressor at 2 bar and saturated liquid exits the condenser at 8 bar. The mass flow rate of refrigerant is 7 kilograms per minute. Determine the following. Alright, so let's go ahead and go, and first let's write down all of the known information. And I've already done that, as you can see in the drawing. Okay, so we'll go ahead and get our drawing bar up, and we'll get started. Starting at state 1 from the appendices table A-11 at 2 bar, H1 equals Hg, which equals 241.3 kilojoules per kilogram. We also have S1 is equal to S at the gaseous state, which is 0.9253 kilojoules per kilogram Kelvin. Now, since compression is isentropic, S1 equals S2, or you could say that S2 is equal to Sg at 2 bars. So we'll go ahead and write that out here so we don't forget. Equals S1, which equals 0.9253 kilojoules per kilogram Kelvin. Now this is when the compressor is operating at an isotropic efficiency of 100%. Now, by interpolation of superheated R134A table A-12 at 8 bar, we can find the enthalpy of state 2. So we go down, and these are the values we use for interpolation by the table. Divided by 4.5. Roll across to equal. We input what we have as our isentropic value. Okay. Now, there's our total interpolation equation, which, when you simplify, give that, it is, look it up a little bit, H2 is equal to 264.15 plus 0.66 minus 264.15 times make this a little bit bigger here. Times 0.9253 minus 0.9066 divided by 0.9374 minus 0.9066, close bracket, which altogether comes out to be H2 is equal to 269.92 kilojoules per kilogram. Now, at state 3, at pressure equal to 8 bar, saturated liquid. So from table A-11, H3 equals H fluid. I'll show you what I'm talking right here. This is all enthalpy, so H3 equals H of F, which is equal to 93.42 kilojoules per kilogram. Alright, now from our known information above, we know that this is also equal to H4. Now we can solve for work of the compressor by equation 10.4. Okay, now that we have all that written down, we can simplify some of the values in here. So we have 7 kilograms per minute. We need this into kilograms per second. So simplify across. 1 minute is equal to 60 seconds. Now we have kilograms times kilojoules per kilogram. So this is going to equal kilojoules per second, or kilowatts. And our known value now, work of the compressor, is equal to 3.339 kilowatts. Okay. Next is the refrigeration capacity, or Qn. This can be solved for by equation 10.3. And it is Q. Now I'm not going to write out again the mathematical steps as I did above because they're the same in the capacity. So all we're going to do is we're going to multiply your mass flow rate, which is 7 kilograms per minute, times 41.3 minus 93.42 kilojoules per kilogram. Okay, so we simplify some of our values. This will give us kilojoules per minute, and our Q in, or heat addition in, is equal to 1035.16 kilojoules per minute. Now, in the previous equation, you can see that refrigeration capacity in tons. So what we're going to do here is we're simply going to go back, and from in the book you can see approximately 211 kilojoules per minute is equal to 1 ton. So we're going to put 1 ton divided by 211 kilojoules per minute. And now our Q in is equal to 4.906 tons. Finally, the coefficient of performance can be evaluated by equation 10.7, and all that is your Q in divided by your work of your compressor. Now, from beforehand, we know that our Qn was in minutes, whereas our work for a compressor was in seconds. So what we're going to do is we're going to take our 1035.16 kilojoules per minute multiplied by 1 minute divided by 60 seconds. All of that over our work of our compressor, which is 3.339 kilojoules per second. And this gives us our coefficient of performance, which is 5.167. And that's all we have for this video. Again, all equations can be found from the Fundamentals of Engineering Thermodynamics, 7th edition by Morin and Shapiro. Thank you.